Welcome to AP Physics 1, Unit 9, the Mechanical Waves Mega Review Packet. We're going to be working through about 40-ish problems, and each of these problems, while it's not in the style of AP Physics College Board style questions, these problems are really good for increasing your comprehension as we work through the material. So as always with these, I've provided the packet for you in Schoology. I encourage you to work through them on your own, or if you're coming from the outside and you stumbled upon this video, I encourage you to pause the video at the beginning of each question, try to answer it on your own, and then unpause and see how you did and compare your answer with mine, unless you're truly stuck, and then at least follow along, watch through, pause it, and then see if you can work back through it on your own. I will try to include timestamps to each of the questions in a comment below, and we'll see how that goes. All right, without further ado, let's get started. So question number 1, AM radio signals. So right now we're looking at a light wave. They broadcast at frequencies between 550 kilohertz and 1600 kilohertz. And hertz right away is a frequency. Whoops, excuse me. Hertz right away is a frequency. So we know the frequencies range from 550 to 1600,000 hertz and travel at just under the speed of light. So what is the shortest AM wavelength? And by the way, the reason it would be just shorter than the speed of light is because it's not traveling in a vacuum, it's traveling in Earth's atmosphere. So what's the shortest AM wavelength? Well, from the equation V equals F lambda, if velocity is constant, we want the one with the smallest wavelength. That would mean we would need the biggest frequency. And they want it in meters, which means we're working with standard units. So we need to make sure that we convert kilohertz to hertz or multiply by 1,000. And again, if we want the smallest wavelength, we want the biggest frequency. So that would be 1600,000 or 1,600,000 hertz times the wavelength equals our speed, or 2.vuja times 10 to the 8th. And then from there it's simple math, and we're going to get an answer equal to 187 meters. Which seems like a very big wavelength, and it is. Most light waves are really small, but radio waves are the biggest of the different types of waves. It goes radio, micro, infrared, visible light. So we go from infrared to red, orange, yellow, green, blue, and to go violet, and then beyond violet is ultraviolet. After ultraviolet, we have X-rays, and then gamma rays are the smallest. So 2 football fields wide is a very reasonable wavelength for a radio wave. Did I skip? Oh, number 5. And no, there is no 2 through 4. They were redacted. So number 5 is 19 waves crash into a beach every 44 seconds. What's the frequency? Well, remember, frequency is equal to oscillations per second, or waves per second. So 19 waves over 44.4 seconds is going to give us a frequency equal to 0.432 hertz. All right, if an ocean wave passes a stationary point every 7 seconds and has a speed of 19 meters per second, what is the wavelength? So we're trying to find the wavelength in meters. So wavelength is unknown. We know it passes a stationary wave every 7 seconds, so the period is, or passes a stationary point every 7 seconds. So the period's 7 seconds. We know the velocity is 19 meters per second, and remember, if you have the period, you also have the frequency, which is equal to 1 over the period, and that's going to be 1 over 7, or 0.141 0.1428, something along those lines. I'll plug it into the calculator in a minute. And then we can plug that into our V equals F lambda equation. And we can calculate the wavelength. And when you plug that in, you should get an answer equal to 133 meters. So can the amplitude be determined? Remember, the amplitude is the size of the wave, and it has nothing to do with the frequency. It has nothing to do with the wavelength. The only thing the amplitude determines is how much energy is contained within the wave. And no information will give you that other than being provided with the amplitude. So not enough information is provided. And similarly, if they give you the amplitude, it really doesn't give you any information other than the amplitude itself. All right, two waves have the same speed. The first has twice the frequency of the second. So same speed, but frequency 2 is twice the frequency of the first wave. And I'm actually going to rewrite that as V1 equals V2. So compare the wavelength. Well, from our equation, V equals F lambda, if velocity is constant and frequency is double, so the second one has twice the frequency, that would mean it would have to have half the wavelength to compensate for it. So that they will still have the same speed. So 2 times a half will give you 1. So now we've gotten ourselves back to the original velocity. So the second wave should have half the wavelength. So not 1/3. The first doesn't have half the wavelength. The first has twice the wavelength. First has 1/3. The second has half the wavelength. There it is, number 5. All right, number 9. The speed of a wave doubles while the wavelength remains the same. What happens to the frequency? So all of a sudden, this magical wave goes way faster. So the speed of the wave doubles, and the wavelength remains constant. So if the left side of the equation doubles, that means the right side of the equation has to double. And if the wavelength isn't doing it, that means the frequency is going to have to be the one to step up and double the right side of the equation. So the frequency doubles. All right, you dip your finger into a pan of water twice each second, producing waves that are separated by 0.19 meters. So there's our waves, and they're separated by 0.19 meters. So that's your wavelength. And there's 2 waves per second, or 2 hertz is our frequency. That was pretty straightforward. Determine the speed of these waves. We have the frequency, we have the wavelength, so then we can plug it in. V equals F lambda, and when you multiply 2 times 0.19, you're going to get 0.38 meters per second. Oh, they didn't ask for that. Oh, that's number 12. So I did number 12 first. I'm so sorry. So 12 is 0.38 meters per second. But now we still have to do number 11, which is asking for the period. Well, period is the inverse of the frequency. So if the frequency is 2 hertz, 1/2 is going to give us 0.5 hertz. It's as easy as that. All right, doing the wave, what type of wave is it? Is it longitudinal or transverse? Remember, transverse, longitudinal. Trans is where the wave is perpendicular to the direction it's traveling. Longitudinal means the direction of the wave is parallel. Well, unless you're bumping into each other back and forth, that's not a longitudinal wave. So it should be a transverse wave. That's where you, everybody stands up and then you pass along the wave. So that's a transverse wave. All right, a sound wave has a wavelength of 5 meters. Whoops. Excuse me. A sound wave has a wavelength of 5 meters, and the distance from compression to the adjacent rarefaction, so we have a compression here going to a rarefaction, and then back to a compression, and then back to a rarefaction. And remember, wavelength is distance from compression to compression or rarefaction to rarefaction. It'll be the same distance, where compression is where the molecules are close together, and rarefactions are where they're spread apart. So they tell us the wavelength is 5 meters, so to figure out from compression to rarefaction, well, that would just be half of that 5 meters. It's 2.5. Oh, I'm sorry, I should clarify. We know that because they told us the wavelength is 5 meters, so if that's 5 meters, then half of that is 2.5. All right, for a given medium, the frequency of a wave, and this is based on definitions, frequency is V equals F lambda. It's not proportional to the wavelength because if velocity is kept constant, if frequency goes up, wavelength is going to have to go down to compensate for it. So it's not proportional to the wavelength. Remember, amplitude has nothing to do with anything, so we can cross out 2 and 4. 5 is inverse proportional to its wavelength. While that answer seems like it might be true, it's actually independent of the wavelength. This is based on definition. Frequency depends on one and only one thing. It depends on the source of the vibration. So in this case, my vocal cords, that frequency, from high frequencies to low frequencies, depends only on how many times per second my vocal cords are vibrating back and forth. And it has nothing to do with the wavelength. The wavelength is a result of the frequency. So really you could say frequency is, let's rewrite it this way. Wavelength is velocity over frequency. So the velocity is determined by the medium it's traveling through, and the frequency is determined by the source of the sound. So it is independent of the wavelength. It depends only on the source of the sound, and those two combined will determine the wavelength. So the wavelength is a result of how the other two are created and travel. So frequency is determined by the source, velocity is determined by the medium that it's traveling through, and both of those together, the ratio of them, determines the wavelength. So the wavelength is a result, it's not an initial thing. One end of a string 7.12 meters long is moved up and down with simple harmonic motion with a frequency of 12 hertz. So 12 times per second they're oscillating their hand up and down. The waves reach the other end of a string in 0.5 seconds. Find the wavelength of the waves on the string. So the string is 0.12 meters, and it makes that distance in 5 seconds. So right off the bat we have a time and we have a distance, so we can find the velocity. Velocity is distance over time, or 0.12 over 5. I should be able to do that in my head, but I'm getting old. 0.024 meters per second is our velocity. They give us the frequency. Oh, it wasn't 0.12, it was 7.12. My mistake. So 7.12 divided by 5, I'm glad I caught that, is 1.424 meters per second. They give us the frequency of 12 hertz. And using that velocity and that frequency, we can calculate the wavelength. V equals F lambda. Super straightforward. But keep in mind, they want our units in centimeters. So when you do that, you should find that the wavelength is equal to 0.119 meters, which we're going to convert to centimeters as 11.9 centimeters. All right, a wave is moving as illustrated with speed v along a rope. That's an interesting looking wave, very sharp moves. That's usually not how they're created, but we're going to roll with it. Which graph correctly shows the relation between the displacement Fs of point P at time t? So P, as this wave moves to the right, P is going to slide up as this wave travels through it. So when this point gets here, it's going to be here. When this part of the wave gets here, it's going to be here. When this part of the wave gets here, it's going to be here. So it's going to go up slowly and then sharply back down as this, and this all reach point P. Correctly shows the relation of the displacement of point P and time t. So it's going to do this a very similar thing. So as time goes on, it gets bigger and bigger and bigger, and then it sharply drops down. So the answer there should be 1. All right, two waves are traveling through the same medium in the same time. So we have wave A and wave B, and right off the bat, I see that wave A is significantly bigger than wave B. Much bigger wavelength. Oh, and that's the question. Compare the wavelengths. A has the longer wavelength. That was a gimme. So now we're using those same waves, compare the amplitudes. Again, amplitude is distance from the equilibrium point to the peaks. So wave A has much bigger amplitude. So wave B has the smaller amplitude. And the same picture for two more questions. Compare the frequencies. Well, frequency is number of waves per second. And these look to be about the same width, but wave B has way more waves packed into that same time span. Especially, through the same medium in the same time frame. So B obviously has more waves per second, so it has the higher frequency. And the final question is compare the periods. Well, period is the amount of time from crest to crest, and it's also the inverse of frequency. So you could approach it both ways. You could say, well, wait a minute, A is going to take way longer for the second crest to get there, and you could say B has a much higher frequency, so it must have a much smaller period. So B has the shorter period, A has the bigger period. So B, or number 4, B has the bigger period. Moving right along tonight, we're doing well. A string with linear mass density of 0.001 kilograms per meter carries a tension of 0.4 newtons. And a frequency of that wave on the string has a wavelength of, so we're trying to find the wavelength. And we know wavelength is velocity over frequency. But we don't know the velocity. That's still unknown. As soon as you see linear mass and tension, you know you're jumping to that velocity equation. And this is the equation to figure out the velocity in a string. It's the square root of tension over the linear mass, where the linear mass is the mass divided by the length. So you could, if you really wanted, collapse this equation to velocity equals the square root of tension over mass over length. But they didn't give us that, so that's actually kind of useless in this problem, and we're going to go with this original equation. And when you plug that in, you should find that the velocity is equal to 20 meters per second. And now that we have the velocity, we can plug that back in to calculate the wavelength. So 20 meters per second divided by our frequency. Was that given? Oh, 100. So 20 over 100 is going to be 0.05 centimeters. do that right? Centimeters? No, that should be 0.05 meters, right? Give me 1 second. As it turns out, I can't do math, and 20 over 100, that's where you move the decimal over 2 spots, is 0.2 meters, or 20 centimeters. All right. Now this one I want to point out, we have option 1, 2, 3, and 4, and our answer choices is going to be a combination of them. So we have to figure out which ones are true, and it looks like 2 of the answers are going to be true, at least based on our answer options. Always use your answer options to kind of guide your thought process. So we have 2 wires, A and B, of equal length that can be used to produce notes where wire A has 1.2 times the mass of wire B. So it has more mass, which means it has more linear density since they're equal length. Remember, velocity equals the square root of tension over the linear density. So bigger mass means bigger linear density, which means this entire side, since this is in the denominator, is going to get smaller. So since wire A has more mass, that means it has a smaller velocity. So as mass increases, the wave is going to slow down, which makes sense. A heavier string is going to take longer to oscillate down the line. So wire A produces a slower velocity. So that takes us down to options number 3 and 4, where the tension is kept the same. So if the tension is kept the same, tension the same, tension the same, then wire B produces a fundamental note that would have to be higher. If A is lower, then B would have to be higher. So 3 is true, which means we can rule out any option that doesn't have 3 in it. So now we have ourselves down to a 33% chance, but let's get that up to 100% chance. So wire B produces the same fundamental frequency or fundamental note. And by the way, a fundamental frequency is just that first note where the wavelength is perfectly fit into the string. So it's fancy for saying that the wavelength is the same between both situations. And from our equation, V equals F lambda, if the wavelength is constant, then velocity is going to directly affect the frequency. Or rather, if they have the same wavelength, then the frequency is going to have to compensate for the velocity. So if the velocity is greater, the frequency is going to have to also be greater. But again, getting back to our thought processes, remember before, if the linear density of A was bigger, then the tension is going to have to be smaller. Or also bigger for A. So if the mass is greater, then the tension is going to have to be greater to compensate for it. But they aren't doing that. They're looking at wire B. So if wire A has a bigger mass, then wire B is going to have a smaller tension to compensate for it. And I'm hoping that's an answer. Yes. And they even say 0.84. Well, if you take 1 over 1.2, you're going to get 0.84. So the answers are 1 and 3. And that is a harder question. So if you struggled with it, I don't blame you. But I would take some time and look through my thoughts once or twice or 4 times and try to make a little bit better sense of it each time. All right, 24, a harmonic wave. Again, the harmonic is where it perfectly fits on the string. A harmonic wave in a wire has amplitude 9.39 millimeters, wavelength of 2.2 meters, and frequency of that. What is the speed? Velocity equals F lambda. We know the wavelength. We know the frequency. so we can figure out the velocity. And when you plug that into a calculator, you should get 645-ish meters per second. I'm going to be more specific, 644.6 meters per second. Ooh, I missed my box. And now they tell us the linear density, which means my first thought process is immediately the velocity equation. Velocity equals the square root of tension over the linear density. We know the velocity now is 644.6, and we know the linear density, but they gave it to us in grams per meter. So you need to convert that to kilograms per meter. Remember, mass always has to be in kilograms. So we're trying to solve for tension, and I'm going to take that and divide it by 1,000 to get it in kilograms, 0.029 kilograms per meter. And when you plug that in, you should algebra your way to the correct answer of roughly 12,000 newtons. That is a ton of tension. Roughly. All right, so now we have a mass creating a tension. And this box is in equilibrium. It's not going up or down, which means that the tension is going to have to equal the weight. And remember, weight is mass times gravity, and weight is a fancy term for force of gravity. And we're going to go ahead and ignore this 9.8 meters per second squared, and we're going to assume gravity is 10 meters per second squared for any and all problems. Always, 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 because that makes the math so much easier with a small percent of error. Even the College Board openly accepts 10 meters per second squared for all problems. So we're going to roll with that. Tension is maintained in a string, and they want us to find the mass per unit length. Oh, the linear density. So they want us to find mu, and the equation that contains that is velocity equals the square root of tension over mu. We can figure out the tension because it's equal to the weight. And were we given the velocity? We were given the velocity. It's 22 meters per second. So the tension is going to be equal to mass times gravity, or 2.8 times 10, which is 28. We know the velocity is 22. And when you plug those in, you should be able to algebra your way to an answer for the linear density equal to 0.058 kilograms per meter. By the way, if there's ever an issue with my math on any of these problems, or you have any discrepancies with how I handled each problem, please put a comment down below. It's tired, I make mistakes, these things happen. You work through enough math problems, enough physics problems, you're going to miss something. But please help me out. If you see something, let me know, and I'll try to write up an annotation saying where the mistake was. Thank you. So what is the wave speed when the suspended mass is 2.9 kilograms? So now that we have the linear density, we're going to change the tension in the rope. Velocity is equal to the square root of tension over the linear density. And we're going to figure out the new speed. Well, tension is increased to 29 newtons, 2.9 times 10, and the linear density should remain the same. The mass of the wire doesn't change, the length of the wire doesn't change, and you can use that to calculate the velocity equal to 70.7 meters per second. Assuming I haven't mathed it up. But it does make sense. We've increased the tension. That should increase the velocity. Ooh, that's a way higher velocity than we should get. It was 22 before? That's a significant increase. I'm going to double check my math. Give me one moment. Math is hard, yo. If you caught that mistake, kudos to you. But that should be only 22.4 meters per second. That makes way more sense considering our initial velocity was 22 and the tension only increased 0.1 out of 2.8 kilograms. So a small increase in tension should have a small increase in velocity. Always double check your answers, look at the original question. In the words of my friend, make it make sense. Two otherwise identical ropes, so nearly identical ropes, but they have a different length. So their linear density must be the same. One is twice as long as the other. They're under the same tension. The wave speed of the shorter rope is, I've pretty much answered this. They have the same linear density, and they have the same tension. And if that's the case, then they should have the same velocity. So it should be the same as that of the longer rope. That was an easy one. If the two ropes that we discussed before are fixed at their ends, the lowest natural frequency of vibration of the shorter rope, so there's our shorter rope, there's the lowest natural frequency, and it's going to reflect back, because remember, the lowest natural frequency is the smallest wave that perfectly fits within the length. We'll discuss that more in depth in the next unit. And there's the one for the one of twice the length. It perfectly fits in. The lowest natural frequency of vibration of the shorter rope is, well, velocity is frequency times wavelength. So they have the same velocity, but the smaller rope, the shorter rope, has a much smaller wavelength, so it has to have a higher frequency to compensate for that. So half the wavelength would have to be multiplied by twice the frequency to still end up with the same velocity. So it would have to be twice that of the longer rope. Alright, a pulse is transmitted down a long string made of two pieces of different materials. So it goes from a thick rope into a thinner rope, and that might not be the case. I should have read more. If the wavelength of the pulse received at the end is longer at the beginning, so the wavelength gets bigger than it was before, and remember, the frequency is going to be the same. So the frequency is dependent only upon the source, even when it changes into a new medium. And this is what we're going to discuss more in depth on the next unit, but at this point it should be, I've said it enough times that it should be starting to sink in. So the wavelength gets bigger. So velocity equals frequency times wavelength. Remember, frequency is dependent only on the source. So if wavelength gets bigger, that means the velocity also got bigger to compensate for it. So the speed in the second part of the string should be greater than in the first. Alright, so one end of a horizontal string is fixed to a wall, so it's tied to a wall, and a transverse wave is in the form of a crest is generated and moves towards the wall. Just as is shown, consider the pulse after it has been reflected by the wall. So the wall is coming in, and this just requires knowledge about the wave. What's true about the reflected wave pulse? Well, if it's fixed, all the energy is going to have to reflect downward, so it's going to come back as a trough. So it doesn't form a crest. It does form a valley, also known as a trough. The reflected pulse doesn't have a greater speed because it's going to be traveling back at an equal speed. It's going to bounce back at an equal speed. So it's not A, it's not C, it's definitely B, and it shouldn't have a greater amplitude. It should be reflected back with an equal amplitude. So whatever amplitude it was coming in with should be the amplitude it's coming back with. So B only, hopefully, is an option choice. And sure enough, there it is. So 25, a pulse moves at 1 meter per second, traveling to the right. At point A, the string is tightly clamped and cannot move. So at that point right there, it's locked in. So after 1 second, it's going to be here. But what's it going to do after that point? Well, if it's tightly clamped, no energy can pass through, which means all the energy has to reflect back. And since it's a fixed point and not a free end to oscillate up and down, it's going to reflect back as a trough. So it's going to be number 2, reflect back as a trough. 33. A series of pulses of amplitude 0.25 meters are sent down a string that's attached to a post at one end. So we have a bunch of waves of 0.25 meters sent towards a post. And they're reflected at the post and travel back along the string without loss of amplitude. So now, and I'm going to change color so you can see what's going to happen, the waves are going to travel back this way. What is the amplitude of the point where two pulses cross if the string is rigidly attached? Well, you have 0.25 meters up, 0.25 meters down. That's destructive interference. So the answer is going to be 0. And that's if it's rigidly attached. But what if it's a free end? Well, if it's a free end, this side can oscillate up. And I'm going to switch to orange so you can see that color. So that means it's going to reflect back, which means you're going to have this orange overlapping with black. So you're going to have 0.25 up plus 0.25 up. The answer is going to be 0.5 meters tall. And that's constructive interference. So we have a complex wave pattern, which is ridiculous. But it's at a rigid hook on the wall. And remember, if it's rigid, it's fixed. That's going to cause the wave to invert as it comes back. So this downward hook is the first part coming in. So instead of going down, it's going to go up. And then this is segment 1, 2, 3, 4, 5, 6, 7, 8. Those are the 8 sections in the order that they will hit the wall or in the order they will reflect. So as they reflect, section 1, instead of being down, is going to go up. Segment 2 is still going to be over. Segment 3, instead of going down, is going to go up. Or rather, did I do that backwards? No, I'm good. And then this, and then this, and then this, and then this. Which is number 2. No, is that number 2? That's not number 2. That's number 5. Matching pictures is hard, yo. So all I did was work my way backwards from the pattern. I flipped it and reversed it. 36. At points in a sound wave, and remember sound wave is longitudinal, where the gas is maximally compressed, well, that's where the pressure is, that's where all the air molecules are packed together. So the pressure is greater than outside pressure. So it's not less than the ambient. It's not equal to the ambient. That's where it's at a maximum. It's definitely not a minimum. And it's not greater than the ambient either. 37. How does sound travel at very high altitudes? Well, keep in mind, air pressure works like a bunch of blankets, just like water in a pool. So the further down you get, the more blankets you have stacked on top of you, which means the more the air molecules get packed together. So for sound to travel at high altitudes, this air molecule is going to have to travel all the way over here to bump into that air molecule, which is going to have to travel all the way over here to bump into that air molecule. So the more the air molecules are spread out, the longer it will take for the molecules to travel and send a sound wave across them. So it's going to travel slower at the higher altitude, whereas down here, boom, 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 boom. When they're closely packed together, the sound wave travels really, really quickly. So it's slower to high altitude, faster to low altitude. So how would the sound travel in outer space? Well, in outer space, there is no air, so there's no way for sound to travel. Sound needs a medium. So sound doesn't travel in outer space. Middle C. Oh! Has a velocity of 1,500 meters per second and 340 meters per second in air. And this goes with the same thing we were discussing in the last question. The more densely packed the molecules are, the faster sound will travel. Water is way more dense than air, so velocity travels faster. That confirms what we were already discussing. So higher velocity, does it have a shorter or smaller wavelength? Well, the question is, does the frequency change? Again, the frequency is dependent on the source. So the frequency is going to be constant. So that middle C has a higher velocity, which means it has a higher wavelength or a longer wavelength to compensate for that higher velocity. And to still have the same frequency. So it should be longer because the speed of sound is greater in water than in air. If the and I just looked at the other answer. This doesn't have to do with the density. The density explained why the velocity is greater, but they didn't ask about that. They asked why the wavelength was longer. And the wavelength is longer because of the greater velocity, which in turn is because of the denser water than air. But they're not asking for that, so we don't need to answer that. 40. If the speed of sound is doubled, how will its speed change? Oh, if the frequency is doubled, excuse me. So twice the frequency, how will it change the speed? And how will its wavelength change? So sound is traveling through air. And we have V equals F lambda. So we have a higher frequency and a lower frequency. Oh, whoa! So the frequency is going to be increased. What happens to the velocity? Well, remember, velocity depends entirely on the medium. So the speed of sound in air is still going to be 340 or 343 meters per second, somewhere in there, depending on the pressure and depending on the temperature. So the velocity is going to maintain constant. So if the left side of the equation is held constant, frequency goes up, the wavelength, again, that's the product of the other two, is going to have to go down to compensate. So it's not that. Speed will not change. There will be no change in speed. Speed won't double. Speed won't halve. So it's between 3 and 4. Wavelength will be cut in half. So equal speed, half the wavelength. A person who talks after inhaling helium gas has a high-pitched voice. One of the reasons for the higher speed of sound in helium than in air. I'm sorry, I'll never do that again. Why does sound travel faster in helium? It's not because it has a greater kinetic energy. Helium molecule has a small number of electrons. Has nothing to do with the number of electrons. It has a small mass. That kind of makes sense to me. Has nothing to do with whether it's in a pure gas, because if you breathe in, what is it, argon? Whatever one makes your voice lower, it's the opposite of helium. It's because helium molecules have very small masses. Think about shaking a small box or a light box versus a heavy box. The heavy box is going to be harder to shake back and forth, but the light box you can shake back and forth really, really, really quickly. So because helium atoms have such a small mass, and they can pack into a smaller area, they're closer together and they're easier to shake. You could think that 2 is true, but that's not actually what's going on. It's not that they're close together. Yeah, that plays a part, but again, frequency depends on your vocal cords. So your vocal cords are what's shaking the air molecules. So if you have normal air, you're shaking the vocal cord this many times per second. But if you're shaking helium, you can shake it way faster, so your vocal cords vibrate faster when you use the same muscles that you're used to using. So it's actually because it has a smaller mass. And the word for that is the timbre of your voice. All right, I think this is going to have to be my last one for the night. And then we'll finish this up in the morning. A small vibrating object on the surface of a ripple tank is the source of waves of frequency 20 hertz and 60 centimeters per second. So we have the frequency and we have the velocity. Source S is moving to the right with speed 20 centimeters per second, as is shown. At which of the labeled points will the frequency measured by a stationary observer be the greatest? Well, where is the frequency the greatest? That depends on how many waves per second are hitting your ear. So this is the Doppler effect. As the source is moving to the right, it creates a pulse every so many per seconds. In fact, 20 hertz. So 20 times per second, or every 20th of a second goes blip, 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 blip. So if you're over here, these blips are hitting you, blip, 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 blip. But as the source is moving away from you, it's going blip, 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 blip. And B and D are somewhere in the middle. Blip, 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 blip. So the one with the highest frequency for the observer is going to be point C. Blip, 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 blip. All right. All right, in the Doppler effect for sound waves, which factors affect the frequency that the observer hears? We have the loudness of the sound. Remember, amplitude is loudness. They're synonymous. So the loudness doesn't change the frequency at all. And that's what Doppler effect has to do with, is the frequency that you hear. As a car is coming close to you, it sounds like a higher frequency because the source is traveling towards you, which means more waves are hitting your ears more quickly. And the frequency sounds lower because as the source is moving away, the sound waves are working against the speed of the car, so they're more spread out. Just like in that picture up above. This is when it's moving away from you, and this is when it's moving towards you. So the loudness has nothing to do with the frequency. So in the Doppler effect for sound waves, which factors affect the frequency that the observer hears? It has nothing to do with the loudness. It does have to do with the speed of the observer. If I'm moving closer to the source of the sound, it does have to do with that. If I'm moving closer, it's going to sound like blip, 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 blip. It's relativity. It doesn't matter if it's moving towards you or you're moving towards it. Both will make the frequency appear higher. Similarly, blip, 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 moving away from it or it moving away from you, both affect it. So 2 and 3 are both true. 35. No, page 35, number 44. A student standing near a straight road records the speed of a car's horn. The frequency recorded as a function of the car's position along the road is plotted along the figure below. The same car made 4 trial runs along the road, so same car is driving past you. M, Z, P, and W are the 4 trials. Each trial was made with the car traveling it at a constant speed. It doesn't necessarily tell us that it was the same speed. So it was made at a constant speed. The 4 results are plotted below, denoted by the curves. So where is the car's speed the lowest? Well, velocity equals frequency times the wavelength. So if it's traveling towards us, that's going to increase the frequency. So up here is where it's traveling towards you, and down here is where it's traveling away from you. So the one that's going to alter the frequency the most is the car that's traveling the fastest. So that has to be car in trial M. 36. The car's speed in trial Z is equal to... is it... Well, it's definitely less than M, because we determined that M was the fastest. And it's not greater than M, and it's not equal to M. So it's less than trial M. That was pretty straightforward. 46, the car's speed in trial P. That looks like it's equal to Z. And we're going to discuss the small dotted line of Z versus the big dotted line of P, or rather, the shallower curve versus the steeper curve. So the car's trial speed in trial P is actually equal to that as it is in trial Z. And the detail actually comes out in the next question. And I'm going to shift this down just a little bit. A car far away before it gets the student has a Doppler shifted frequency which is higher than that of the car's horn's frequency. Whoa. Doppler shifted frequency, which is lower than the car's horn frequency. The average of these two frequencies is what? Car far away before it gets has a frequency which is higher than the normal frequency. Of course. A car far away after passing the student has a Doppler shifted frequency that's lower than the car's frequency. I agree with that too. The average of the frequency when it's coming towards you and the frequency when it's going away from you should be the average frequency. And let's look at it. We have about 1,000 for M, which goes down to 800. If we average those, it's right around 900. If we look at car P, that's about 960. And it ends at about 840. And the average of that is, again, 900. So the average of the frequency coming towards you and the frequency away from you is equal to the horn's frequency when the car is at rest. In the different trials, by the way, I want to point out I'm not positive on this answer, but it makes sense to me and the graph seems to confirm my suspicion. So if you know better than me, please double check, do some research, whatever you need to do. But I feel okay enough on that question to move on. 48. In the different trials, the distance of the student on the road sometimes varied. So as the car passes on this road, sometimes the student was really close and staying on the side of the road, and other times the student was really far away. Now, this doesn't seem like it would have an effect, but when the student is close, the Doppler effect, the car is immediately traveling away. So when it's really, really close, it's a sharp change in the velocity. And that's actually going to be trial Z. But when it's really, really far away, the distance between them and the relative velocity for person P, the relative velocity is going to change at a more spread out rate. So that's actually going to be trial P. So which trial did the student stand closest to the road? Well, that's trial Z. And that's another question that I encourage you to go back and look at how I explained it and look at it a second time and listen to it a third and fourth time and try to make sense of it. And the more times you listen to it, I think it'll make more sense. But let's say a car is going 100 miles per hour. When it's really far away, it's going to be traveling 100 miles per hour relative to you. But as it gets closer, since it's a far distance, this triangle speed, the horizontal component is going to seem to change at a less dramatic rate than if you're the orange person standing on the side of the road, because that's immediately going to go from positive 100 to negative 100, or directly towards you to directly away from you. So Z is the person standing right next to the road because it's such a sharp change and not a drastic change like in P. And the final question, holy smokes, that's a lot of answer choices. John is listening to a horn. He knows the frequency of the horn is that when both he and the horn are at rest. If he hears the horn's pitch at a higher frequency, which of the following is possible? So if it sounds like a higher frequency, they're moving towards each other. One or both, either way. So both can be moving and have the same speed. Sure, they can be moving towards each other at 20 meters per second. So that's possible. A is absolutely true. Anything without A is wrong. So we can automatically get rid of 2, 3, and that's it. But we've gotten rid of 2 option choices. By the way, I want to point out we have 1 through 7 over here and 8 through 10 down here. Both can be moving while having different speeds. Of course. I could be moving towards him at 5. He could be moving towards me at 10. So we can both be moving and both have different speeds. So B has to be true as well. But it seems B is an option choice in all of them except for 8 and 10. So we've got rid of 2 more answer choices. John can be moving towards a stationary horn. Absolutely. They're moving towards each other in some capacity. That's what this is all boiling down to. So C has to be an answer choice. That actually got rid of nothing. Okay. D. The distance between John and the horn is increasing. That means they're getting further apart. So D is absolutely 100% false. Anything with D is out. D, D, D. So anytime you see a D, you got to get it out. E. Both can be moving in the same direction. Sure, I could be moving 5 meters per second this way. He could be moving at 100 meters per second behind me. We're still getting closer. So E can be true. So we got to find E. Anything without E is out. What did I just cross out? Oh, anything without E is out. We want E. We want E. So that gets rid of 6. And now we have 2 options left, which hopefully F will eliminate for us. Both can be moving, but away from each other. Absolutely not. They have to be moving closer to each other for the frequency to sound higher than it truly is. So F has to be an option. That gets rid of 4. That means option number 1 is true. A, B, C, E, F. That was a brutal final question. For those of you who stuck with me through this, congratulations. You're now better at physics. I hope you paused it, attempted it on your own, or if you didn't, fine. Re-download a blank copy of this document, or work your way through the video again and pause and try to do the questions again completely on your own. Challenge yourselves. The more you do this, the better you get at it. That's how physics works. Physics takes practice. It's not something that you just glance at and get. It takes repeat learning, staggered learning. But either way, I hope you guys stuck with me through this. And I hope you have a great day. Thanks. Bye.